Let's talk about some of the harmonics. In another video, we talked about what happens when it reaches a boundary. So if I have a wave that's traveling along here and it hits a fixed boundary here, that the wave will invert. So it's going to head towards it. It's going to hit the boundary here. If this is fixed, then the wave is basically going to come back on the other side and head back this way. So it will invert. If I send a second wave, and then we also talked about if I send a wave this way and a wave this way, heading towards each other, they will, when they will combine to something big and pass through each other. And so then passing this way, passing that way. Or if they were on opposite sides, so this is constructive interference. And then if one were going that way and the one were inverted, going that way, when they meet, it would flatline, and then they would pass through each other. And this is destructive interference. So if I send a pulse down to a fixed end and it comes back like that, then if I send the next one down, so if I send a second pulse down, it will interfere with the first one. And if I do it right, what I'll end up with is a harmonic. So I will get it so that I'm sending waves down, I'm sending waves back, and they'll start to interfere with each other. And if I'm doing it at the right frequency, given the right speed and the length and everything else, then I'm going to start getting a pattern here. And so I can get what is known as a standing wave like this, or I can get one like that. That should be in the center right there. Let's see if I can draw that a little bit better. That's a little bit better. And I can get these various standing patterns. And there's going to be a video out there dealing with the, there is a video out there dealing with the string vibrator, which you can check out. And actually that will be potentially a lab that you're going to do. And so this is known as the first harmonic. This is known as the second harmonic. Also, some textbooks will call it the first overtone. And then so on. Then you get third harmonic, fourth harmonic, and so on. So if I have a string of length L, then my first harmonic, so first, well, think about how many waves that is. A full wave, if you look at a full wave basically goes up, down, and back. That's a full wave, or that's a full wave, so it goes all the way back to where it started, starting point, and going in the same direction. This right here is known as the antinode. These points right here are the nodes. And this is the string vibrating back and forth very quickly right here. So, but that is a full wave right there. And so if I have my first harmonic, well, that's just half a wave. So my length is equal to half of a wavelength. In other words, my wavelength is equal to 2 times L. The second harmonic, that's a full wavelength, so my length is equal to the wavelength, so the wavelength is equal to L. The third harmonic, now because they're fixed, I have nodes at the ends. This is 2 fixed ends. So fixed end, node. So that is 1.5 wavelengths. Notice I'm adding a half wave every single time, and that pattern will hold. And so the wavelength is equal to 2/3 L. And then the fourth, something like that. They should be equally spaced. So this is equal to 2 wavelengths, or the wavelength is equal to 1/2 L. If I have a fixed and a free end, think free end as an antinode. So one fixed, one free. So that will be a node, and that will be an antinode. And we will do have another lab on that one. Well, at least we'll have video on that one. So one fixed, one free end. The simplest pattern is basically that. So this is my fixed end right here, and this is my free end over here. This is an antinode. This is maximum vibration right here. So the string is vibrating back and forth very quickly here, and it looks like, physically, it looks like a blur. If you watch the vibrating string video, you'll notice that. And so this is vibrating back and forth very quickly right there. So this is, though, and I want you to think about it first. I'm going to take a breath here and then come back. All right, I assume you pause it if you needed to. That is a quarter of a wave. And so the wavelength is equal to 4 times whatever that distance there is. We'll call L. That's the first harmonic. The second harmonic, I need to change my vocabulary there. I've been calling it second harmonic for years now. That actually is the third harmonic. There are no even harmonics on this officially. So third harmonic, then fifth harmonic. The harmonic, this number right here is the multiple of that, and we'll show that in just a second here. So that is 3/4 of a wavelength. In other words, it's 3 times that. That's why it's the third harmonic. And so the wavelength is equal to 4/3 L. And then the fifth harmonic, it's 5/4 times the wavelength, or the wavelength is 4/5 times L. And then the last situation we deal with harmonics is 2 free ends. And a free end means an antinode, and the simplest pattern I can come up with is that. If that distance there is L, recognize that again the full wave looks like that. And we are basically looking in this range right here. So this is a half wave. We just basically cut the ends off. So L is equal to a half of a wave. The wavelength, therefore, is 2L. That's the first harmonic. The second harmonic, that is drawn horribly. Let's see if I can draw it a little bit better. That's better. The second harmonic, that's a full wave. Because we start here, we end up back where we started, going in the same direction. And so lambda is equal to L. And we're adding, again, half a wave every time. So the third harmonic, well, that's a full wave to there, and then we added a half a wave, so L is equal to 3/2 or 1.5 waves, or wavelength is 2/3 L. And we will indeed do a demonstration with that. But notice the math here is the same as the math we had here with the 2 fixed ends.